This is not okay. That works. We don't need this.
Yeah, you don't need that.
Right.
Everything should be okay. Okay, we're live.
I guess I got one here.
Oops, they went out for some reason. I think
Say
is it maybe the screensaver?
There. Guess right there.
okay, great. All right, can we start? Are we all here? Okay. So today I'm going to talk about sparsity and how sparsity can help continual learning. So the big question is, does sparsity help continual learning? We know that already a bit, so there are a couple of papers pointing out in that direction. It is kind of intuitively right, in the sense that you have less patterns and representations colliding with one another, and probably that also implies, especially if we talk about sparsity in the weights, we are talking also about the less interference among weights. So I guess it's easier to pack in a single model different concepts and skills, knowledge. So that's something we want to do in continual learning. I don't know if that automatically leads to generalization. That's an interesting topic we could investigate in the future. But essentially, in this brief presentation, I was more focused on a simple application of sparsity on the representations with a k-winners implementation that you guys proposed in the paper also dance. And so actually it's just a very simple experiment. There are just a few experiments with very few hyperparameters involved and dimensions considered, but I guess it's just a start, and with your feedback we can build on top of this. So basically the benchmark we are considering is remitted and NIST, which is not, at least from my perspective, a great benchmark for continual learning or in general, because it's very small, it's easy to overfit. There are many reasons why maybe it's difficult to scale results with bigger networks and other data sets starting from this one, but it's used by the research community, the continual learning community. And of course it's easy to start from here. You can run these experiments on laptops, even I run them on servers, and it works great. I mean, in a few minutes you get the results, so that's why.
So can we think of this as more like a debugging exercise?
Yeah, it's what like I was set up in the basic routines and functions, the Codebase and everything, so it was easy to start with this.
Right. But from what you're saying, it also seems like we shouldn't generalize too much
right,
on these
absolutely.
results.
That's my warning, my big warning here. That's these results that I'm going to present are just not multi-run evaluations where I change a lot of things. I care a lot of, I take into account a lot of hyperparameters. It's just a few glance, let's say, on this problem, and starting point for everything else. And maybe it can trigger a few interesting questions and discussion. That's really what we care about, right?
Vincenzo, would you turn that light off?
Light
on the
off?
wall over there.
Okay.
Clearing. No, the other one off.
Right.
That's it. Yeah, that's actually
okay.
better with the.
Is it better for us?
I
think that's a more important question.
If you like, you can turn it back on. We can.
The farthest away, and I can read fine.
You're okay?
So,
the overhead light's okay, bro. You can turn that on.
okay, thanks.
Okay.
That's good. For me, it's
I don't know. I always have problems with lighting.
Yeah.
So for those of you, I guess all of you know, well, for this guys on streaming, for those of you who don't know, the MNIST dataset is a classification. Essentially, is a very small dataset of handwritten digits, and this is the base on which we're going to build our permitted MNIST task. That essentially is a fixed permutation applied on the basic dataset, MNIST dataset, which means essentially that on each image we scramble the position of the pixels, but we keep that, repositioning essentially the same for all the images. So we are just, I don't know, change the position of one pixel to another position that's fixed for all the images. So essentially we are just creating a new distribution for the data set, but it should be, it's very difficult for us as humans to recognize digits this way, but it should be kind of the same complexity as recognizing normal and written digits for machine learning model. Okay, so and what we do in this benchmark is to create 10 different training set and test sets with these fixed permutations, so 10 different permutations. And the idea is to train a single model to distinguish these 10 digits and generalize across these multiple sub-distributions, I would say. So we start with the first training set, we learn about this distribution and to distinguish these 10 digits. Then we move to the second one with the same model. We would like to generalize our ability to discriminate digits on two different distributions, they're very different among each other, but still trying to generalize this understanding in a single model. And we can do that for 10 different tasks. So as we are subject to catastrophic forgetting, as we don't maintain, essentially, when we move to the second task, we don't maintain the training data of the first task in memory, we don't retrain on that. As we try to learn about this new data distribution, we completely erase, or at least we erase part of the ability to recognize digits in this previous distribution of task one. So that's the setting of the problem, the setting, and the problem we're trying to tackle, catastrophic forgetting. So again.
Yeah, how is this different from just taking a completely new random set of inputs and saying, okay, this random set is class 1, this random set is class 2, this random...
like random noise in the images? Images. So the fact is that
this permutation is kind of really scrambled.
Yeah, but it's, the important part is that it's fixed.
But does the network use that? Does it
yeah,
learn the permutations?
that's very... the fact that this a fixed permutation for all the images is what creates the, it gives the network the ability to recognize these images, otherwise wouldn't be.
But is it faster to train the second one than the first set?
So, well, in this setting, this is something different from what I told Marcus in the previous meetings, sorry for that, but actually, this is not the first task, so for all these tasks, what I do is that it is a different permutation. So
okay, so it never seems like a normal digit.
Yeah, not a normal digit. So that it's really the same. It's really the same complexity.
Right, but is it faster to do TR1 than TR0, or is it faster to do TR9 than TR1?
So for now, I'm considering just a fixed number of epochs for every task. So, but I guess after, especially from the first to the second one, it's easier to learn the following tasks because we have a bit of. Yeah, we can go into this maybe very shortly, but essentially the problem with the permuted and missed task is that when you have a model, let's say that, well, it can be any kind of model, but let's say it's, let's say that this is our model with, many layers possibly, then when you learn the first task, you learn all these different features, hierarchical features, with hyperpropagation, all that is great. But then when you move to the second task, what happens is that you just want to learn the permutation, actually, to reposition it, essentially. You can do that, and in general, I think that networks do that, so that you learn just a new mapping here, how to do this permutation. And then the rest of the network can be pretty much fixed.
I don't think that's possible, because the lowest convolutional layers are just looking at small local patches, but the permutation is global throughout the image. I don't think
so in the multi-layer perceptron ones.
Yeah, right.
In the multi-layer, in the CNN ones, at least the lowest layers
right.
can't do it. But in the MLP.
But yeah, the general idea is that you can exploit. Also, in these very strange case of permutations and not natural images, you can exploit the information somehow.
Yeah, I guess in the MLP case, these permutations are the pre-muted data is fundamentally the same as the original data.
Right.
Yeah.
It's not like the first one, the actual two on the left there is easier for an MLP than
Yeah.
the one on the right. They're
Right.
the same.
Right.
But for CNN, there's a huge difference.
Yeah, and also, I'll say that in a second of the models that I'm considering, but for a CNN, you know, the permuted essentially images are, you know, there's not really an advantage in using CNNs here. That's just saying that I tried.
Locality.
Yeah, there's
Yeah,
no,
there's no
we destroyed,
locality.
you know, the
The spatial coherence, all the
combinations
things.
and
Right.
features. So I mean, I'm using here CNNs as well because I want to try them out, but I guess we have to scale up the benchmarking or considering the split and mist in which we have different tasks in which
Right.
we try to classify 2 digits for each
Yeah.
task.
Yeah.
That's a possibility, and then moving to cipher or something else because it's, you know, trying to do these experiments was very difficult. It disentangled several factors, and I guess it's just better in these cases when it's you have a very high search space. It's just better to stick to the problem that you actually care to solve, like even bigger, and try to find a heuristic or something that can work in that specific case. Otherwise, trying to generalize these ideas and results to every possible data is going to be difficult, especially when you start trying new ideas. Well, we'll see about that. So again, so I guess the training protocol is clear enough. So we have these 10 different tasks we train one after the other. And for the test part, what we want to do is to test essentially our model in every time step on all the possible tasks, so that we have an idea on how the performances in recognizing these digits are across time and concerning the specific sub-distributions that we train on. So I mean, in this case, again, it's not really helpful in terms of thinking of, for example, forward transfer, so that if we are learning about this task, T1 is that it has an effect on other tasks that I've not encountered up to that point. That's an interesting question for, you know, AI systems in general. I'm going to be these learning how it is affecting, you know, future things that I'm going to encounter, and if I can exploit this new knowledge that I just gained to solve new things. But in this case, of course, you know, what we are learning about a specific subdistribution is not really transferable. You cannot easily see that from the graphs and plots I'm going to show you. Essentially, the performance is not great in that sense, but we can still assess, you know, always looking at the accuracy essentially on all the tasks can give us an idea on how forgetting is happening in every different task and subdistribution. So we can see, this task in this case, we're learning about this permutation, and it has affected a lot this particular task in this particular moment. It can be interesting to look at. So this is the setting in which we are operating, and then what I'm doing here was to try. I tried several different architectures, but in the end I stick to just 3 of them, just for the sake of clarity. I mean, it's very interesting the results I'm getting, but it's difficult to generalize to a very broad understanding of the things that are going on. But essentially, I'm considering 3 models. So 2 MLPs, one with just 1 hidden layer. So we start from a linearized input. So essentially, we are just linearizing that image 28 by 28. And we can do that because we're not exploiting in an LLP spatial, the 2D, let's say, arrangement of the pixels. And yeah, in this case, we consider 4,000 hidden units for linear layer. I also tried with different dimensions here, like 1,000, something like that, and it works. But in this case, was really this particular. As we're going to see next, this particular case was really fun to look at. It was very strange and weird. The results are strange. And so I stick with those. Okay, I consider two versions of them. So the sparse version and the dense version, just to compare how we are really sparsify the network and how the introduction of k-winners here can affect the final results.
Do you use sparse weights at all?
No,
Or no?
not in this
Oh,
area.
okay.
No,
Oh, that's
just
really-
sparse. Yeah, that's another. I mean, I tried one time on this model, but then it's very. If you don't have like a dynamic sparse thing, then it's very difficult to have a very fixed set of weights that you use for all the tasks. So I guess
Did you try it or?
Yeah, I tried.
Okay.
I tried it, but
Sparse weights.
it was. I don't remember exactly, but it was not. It was difficult at least. I just decided that I was going to just for this first part of the experiment just stick to the k-winners. It was easier.
Okay, because the nice properties that we want from sparsity
Yeah.
really only happen if you do sparse.
Yeah.
And if you do sparse dense multiplications, you don't get into those really nice exponential drops in
Yeah.
error and stuff like that. So the real beauty of the sparse representations for continuous learning and avoiding catastrophic forgetting is going to happen when we're doing sparse.
Yeah.
I'm curious, is that coming from like the combinatorics? Is that coming from like empirically you've seen things get better? Are you talking from a computational standpoint? I'm curious where
No, I said from a mathematical standpoint.
Mathematical,
Yeah.
okay, cool.
So if you look at the SDR math,
Yeah.
if you keep one side dense and the other sparse, you don't get that exponential drop off.
So, for example, in this paper that was out, I guess it was accepted by Hiller, self-forced continual learning we analyzed in the past. They were arguing that essentially, in the end, they proposed something just about the sparsification of the representations. So, like in this case, just using k-winners or another strategy. In that case, was an addition to the loss function of a regularization term to
Right.
avoid the dense activations, but they were arguing in the paper that essentially that can somehow also imply a sparsity in the weights somehow. And it was like we have to look at that.
Yes.
If the math is pointing in that direction, I guess it's right that we have to integrate it.
Yeah, it's just sparsity will still help.
Yeah.
But it's to get into this really beautiful regime of these
Yeah.
exponential drop-offs. And mathematically, you really need high dimensionality and sparse computation.
Yeah, I'm gonna add that dimension to the problem here. It's very interesting. It's just that I guess in this kind of problem it was not helping much. Well, we'll see.
Maybe more than 4,000 units now.
You're blowing up the representational space perfectly.
Yeah, this is. I mean, it's quite common that you want to have in NLPs, very great, big hidden layer in general autoencoders, whatever. It's very interesting to have a sparse, not big in terms of a dimension.
It's still different. You could solve it through.
Absolutely. In fact, we're gonna see then the actual active units. And
50 times bigger than it should be.
yeah, but I mean, it's still important to. It's when you are in a big space, it's easy to disentangle things, right? So
That's
That's the
part of the
main-
intuition.
the main.
Exactly.
Okay, so then the second NLP is just a multi-even layer perception. So I just reproduce again this pattern of linear k-winners and dropout again, and then I have the output layer of 10 units as we are classifying 10 classes, 10 digits. And then for the CNN, I tried just a simple CNN with just one convolution here with 64 channels, 5x5 kernel. And in this case, I use ReLU, k-winners, and dropout. Linear of just 512 ReLU, k-winners, and dropout. I know this is not something we are doing, but then we are seeing a relation study when I try to, from this configuration, the CNN, I try to remove things, and I see that in this case, ReLU is helping a bit.
So it's ReLU followed by k-winners?
ReLU followed by k-winners and followed by dropout.
And what's the percent on that you're using for k-winners?
So now we're gonna look into,
Okay.
into the results, and in that case, I keep track of all the
Okay,
errors.
because for in many cases, the value should be almost like a no-op.
Yeah.
But it depends on your sparsity, I guess.
It also depends on if you're using dash norm. Because that term will center stuff on zero.
Yeah, right.
And then k-winners makes it, so if you're not using that term, you could have a ton of negative values.
Yeah, yeah, that's what I was thinking, that when you use just k-winners, you're also probably passing some negative values sometimes. And that, how that is gonna impact on the gradient descent in optimization. I mean, in general, if you think of the k-winners as like, I don't want my activation to go up to a certain point, so it's like a upper threshold to what you're saying, it shouldn't be activated that much. But in the end, you're keeping free. If that's not it, you just keep free. You let the gradient descent algorithm do what it as we will normally do, right? So that's a possible idea, but.
Is there some reason why you didn't try using max pool?
So again, in many convolutional networks now, we don't use max pool much anymore. But it was interesting, especially from this, it introduced a bit of somehow, it's a kind of sparsity in the sense that you are essentially removing some activation somehow if you're
Yeah, but you're condensing it.
You're condensing,
You're not.
yeah.
You're compressing it. You're not really introducing sparsity. Sometimes, yeah.
well, but I mean, in general, in state-of-the-art convolutional network, we cannot find max pooling anymore, layers anymore. So I guess that's one thing. Yeah, I mean, we cannot many different dimensions, but every possible dimension is.
No, but essentially, at least these are very simple
Yeah,
things
yeah,
that you're
exactly,
just testing
exactly,
out, right?
exactly.
Yeah.
Okay, so these are the models I consider, and then we're gonna see a little operation study where I remove these features one by one, and we try to see the impact on these on the final results. So momentum, L2 regularization, real activation, dropout, and k-winners. When I say I remove k-winners, I mean just removing the local version.
Oh, okay, so it's still k-winners. but it's-
Yeah, because without k-winners, you end up with the dense.
Well, K-winners and purple only for CNN, right?
K-winners only for CNN, right?
K-winners
Because
only
it's
for CNN.
it's like k-winners to the local.
Right.
And so yeah, because it was working better, so I just changed back to
K-winner within the kernel size.
Yeah.
Yeah, so instead of performing it, so the one that I implemented here, that I put here, is the local version. So it's sparsely is computed across channels and not on feature maps.
That's not the equivalent of local inhibition, is it? I mean,
It's pretty similar.
Yeah,
It's very similar. Yeah.
But the reward is different, the way because gradient descent is being applied, right? Or am I wrong there?
Yeah, in all these cases, we're using gradient descent,
Yeah.
which is different from the
Yeah, but
special
it's
pooler.
the basic idea is that you're in the same receptive field, we have different features, maps, and we want essentially these to compete somehow, so that the feature map that is the feature that is recognized most is the one that is going to be activated, right? So the top. Okay.
But this is orthogonal to everything gradient
Yeah.
descent. This is just the activation function.
Okay,
We
yeah.
have a set of units.
Okay. Well, I think I'm done with the whiteboard. Not again. Okay, let's put it back. Sorry about this.
No, I was afraid it was going to get ignored.
Okay, so this was just also for me. I mean, I also put some ideas here and references. I guess I can share these notebook with you as well, so it can be like a collection of material as well on things that I'm doing. But yeah, this is something I already discussed with you. There are a couple of papers here, titles actually, that you can look at. I think they are very aligned somehow with what we are doing here. So this idea of sparsity and continual learning somehow. So this paper, essentially from 2012, was one of the first papers introducing the permuted MNIST task and also let's say in a continual learning setting. I guess it was a paper from Smith Uber, so it was great. I mean, one of the first ideas on but also sparsity. It's the idea that units should compete among each other, and in that way you can have some kind of branch selective plasticity. So it's interesting. That was the whole idea around the paper, and they were explaining that it's important to have this competition among units so that you can learn things continually. So it was interesting. I should read it again. Okay, so this is the task we have seen. So we're gonna just import some things here. It's just for tables. Okay, so here I just wanted to show you the actual images, but it's something we can see also on the whiteboard. So I created a continual learning MNIST class so that we can have with a single class we have this continuous stream of data. So in this case, I just take from this data set. You can take out all the training sets, and what I do here is just plotting 4 images. Yeah, here is starting permutation. But yeah, so these are the original images, and these are the first task images. Actually, this is a 5 here, down here. This is a 0. This is a 4. This is a 1. So just to show you how the original images are transformed.
It's like a hash or something?
No, it's just a random permutation of the order.
Oh, okay.
I'm wondering, can humans start to recognize if you see a lot of the same?
I don't think they can.
No, because all our vision relies on locality.
It's very difficult.
The pattern recognition is tied to these.
Topological associations.
Thousands of characters are they gonna look like? I wanted to see 2, 3, 4 permuted ones just to see how it looks like in this. Because
We can.
You want to see if you can try to learn that?
Yeah.
I think it's very. Yeah, but I think
We
it's
could
very.
learn it if we mapped it onto random logical symbols that don't make sense, but
Yeah.
look like.
I think what you could learn is a number.
Yeah, like ones would look like this somehow, right? Like other ones, since the permutations are fixed, other ones would look like that.
Yeah, that's true.
But if you solve this, you solve AI, so you should do that. Okay, so essentially the dimensions we are talking about are these. So we have 60,000 images for the training set, 28 by 28, and then of course we have also these labels, the same number of labels, and 10 different tasks. So for each task we have these dimensions, just for making it clear. Okay. Okay, so again, these results should be, taken with a grain of salt, in the sense that we should actually run. So first of all, they are not really deterministic. So when you run these results on GPUs, and you accumulate essentially the errors or the shift across 10 different tasks, you can end up with different results. So a few percentage points difference, like 1 to 3. So it's something that you should actually do in general, as in a multiple run, average way. And then we should also consider different permutations and different orders of these permutations. So that's just to clarify that. So I don't know if you want to look a bit at the code base. I'm going to release all this code, in a GitHub repo later on. But essentially. Can you do that? Let's see.
0.01%.
How can I switch the
What are you trying to do?
I can try to switch the window that is shared through Zoom. No.
So
Here, maybe no.
See where it says staff share. If you move your mouse there, I think you'll see buttons appear.
Where?
Up to
The
the
green bar.
Okay, the green bar. So okay, great. So new share, I guess. Yeah, but I can see. What? What's up? This one.
Right,
So I
you can
want
click on the right
to.
screen.
But I don't remember what.
There you go. The bottom
This
title
one.
Oh, that one.
You see that? Ah, okay. Maybe
I
I just.
see your code now, yeah.
Right.
Okay. Well, just to quickly show you the idea of the organization of this code base. So I split the entire code base in different directories. The first one is the benchmark, so all the code related to the benchmark is here. So what I do in general when I try to work on these projects is to have continual learning, especially. I have like the basic util stuff in a single class that in this case is MNIST, and then I have a continuous version of it in which I can create an iterator that I can use like very easily to go through all the possible tasks and have a couple of functions that I specifically use for continual learning. So this, for example, class is already made so that it can handle both the split MNIST and the permuted MNIST, all these variations. So this will be the directory on all the benchmarks that I'm going to add. Then we have I have a directory with the experiments parameters. So in this case, I use the standard config as you also maybe Subodha you used for the also dance paper. So I guess this is great as well. I used in the past the Sacred tool that already keep tracks all the parameters and variations and save them in a repository. But I guess this is very nice. Very easy.
There's lots of different ways of doing it. And,
yeah,
we can do dicts.
But this
like
is great.
locusts way.
The only fact that I'm a bit the only tedious thing I think is just use these functions to convert every possible Boolean, and that's a bit annoying.
No, you don't have to do that.
No, what I do here is I have for the when I choose the configuration, I do like, for example, I want a Boolean, I have to use this function.
No, we don't
need
to do that.
Ah, right. So maybe there's a better way. But
you could also do it directly as dicts in the code if you want. That's
right.
another way that
that's
Lucas
fine.
has been
That
doing it.
makes better. Well, okay. But again, what I do here is to have all the experiments, all different config files, so that they can be in a single place. And then I have the classes implemented. In this case, is based on PyTorch, just PyTorch and newbig.research and newbig.torch. So these are the main dependencies, I would say. And I have just two different classes for the a general, CNN, plain CNN, and a general NLP. And then I have a directory with the results. So in this case, what I do is very simple. Is just to save all the results in a pickled file, and then I will load these into the notebook now to plot all the stats that I collected about this. So this is one way of doing that. So with Sacred, the nice thing of Sacred is that all the things you could store them in a MongoDB, and then with a notebook you just pick from the MongoDB record of the experiment all the things that you have saved about that. So that's nice.
What did you say was?
Sacred.
Sacred.
Oh, okay.
This approach is the first.
It's a replacement to Ray.
Like using a MongoDB.
Yeah.
And it's also very easy to set up without Sacred.
So, but the nice thing of Sacred is that it has a lot of functions and features. Like I want all these, for example, the snapshot of the code to be stored as well. Easy, just one flag. You want to record all the state of the machine in that particular moment. So how was the workload and stuff. I mean, it's about the reproducibility. So I guess it's more. Or I don't know. All the for example, one thing that's very difficult for machine learning model experiments is that you have a lot of artifacts. They call it that way in Sacred. But this idea that, for example, I use pre-trained network weights. Okay, my code is well, stored somewhere. I know how to reproduce the results, but it depends also on an external file. That I want to keep track on that as well if I want to reproduce the results. So that's to consider as well. Okay, and then I have an utils directory here with a few PyTorch and common utils. So that's what. And then I tried to integrate Ray, but it was a bit tricky for continual learning in general, and so I put that on hold because I don't really need it now. Maybe in the future, if I want to explore many hyperparameters, that's one of the big
They have a
advantages, I guess, of
separate
array.
version for continuous learning.
They have a separate version? Wow.
No, for reinforcement
That's
learning.
reinforcement.
For reinforcement
Oh,
learning.
reinforcement learning.
Ah.
Oh, yeah, that's right.
But I can have to set up.
Yeah, right, because it's not that straightforward. I mean, it's the whole concept of array was based on the idea of training on a single, one shot, going through the epochs, and so I need to understand.
But you can do it, it's not that hard.
Yeah, I guess so. But yeah, for now I don't need it, so I have this very simple run mlist file, which I can choose my configuration, and what I do is essentially load all these configurations and then define my model, and then the optimizer, and here I use my my dataset, and I can navigate. This is essentially all the code that matters for continual learning. No, actually, yeah, this is for the stats, but essentially this part. So with the dataset with an enumerator, I can go through all the training tasks like this very easily, and then I have a trainnet function that is like an utility in PyTorch, so it's all developed there. I mean, it was something that I've written, so that it's very easy to have a single main file that is very easy to compare. Okay, so this was it. Then we can go maybe in another meeting or something through all the possible things in this code base. But I guess with this very simple introduction, you can already, when I share you the code, you can already take a look at that. Okay, can you see that? Yeah. Good. Go away. Okay, so
I can't see this now.
can you see this? No, no.
Yeah,
Okay,
I'm
we have
still
to
seeing
share
yours.
that. Okay, great. So the new share, desktop to, I guess this.
Yeah.
Let's try it.
There we go, thank you.
Great. So okay, what are the parameters I'm considering here? So these essentially parameters, they are modeling the specification part, the model part, and the optimizer part. So for the specification, it's very easy. Just a parameter here, which is gonna tell how to construct the model. So these different architectures that we have seen here, if essentially we are gonna add k-winners or not to the model. Then we have a few parameters that you well know, that are the parameters for the k-winners. Actually, in this case, these parameters are, I use these parameters as fixed for the experiments. So this one.
That is a very low percent.
Yeah.
4,000 units, that's
Yeah, well, we don't look at the exact numbers for now. These are just we see about the specific parameters of each experiment. These are, I don't remember. Yeah, I mean, I just
Right.
I don't. But it's true that in the following experiments, I'm going to use a very low percentage. Okay, so. Okay, but essentially what I'm doing here, I hope this is correct, but what I'm doing is like disabling boosting, right?
No,
No?
I don't think so. You have to be boost strength 0.
Right.
That's interesting. So because I asked Michelangelo about this, but what I thought it was that boost strength was the multiplier for the activation of the units, right?
It's
So
an exponential.
Okay.
Someone recently
Okay.
talked about this in the forum too, there was a
oops.
question about it.
I mean, I think it says it in the comments.
It's in the document.
Yeah,
It says
yeah.
0 means turn
I
it
mean,
off.
the
Yeah.
actual formula in the document, like
Yeah.
But it also says in the comments, use 0 to turn it off. which is-
Okay, so it's my fault, but so essentially the experiments that we're gonna see here are with these parameters of boost.
Okay, which is going to fight against continuous learning.
Okay, so this is the first thing I'm going to,
spread them out.
Oh, interesting. This is the first thing I'm going to try actually, so
Okay.
is to see if the results are still the same.
Did anybody see recently the post Marty did on the sort of a parameter search grid, and he used boosting as one of the parameters he searched through, and his best performance was somewhere between like 0.1 and 0.3 for boost strength. Yeah,
Also one that's actually off.
yeah, seems to be.
Okay, so and then for the for the model part, I have the parameter to say it's a CNN or not, and then the number of hidden layers and hidden units, and the dropout parameter. For the optimizer, we have the learning rate. If we use Nestor as a kind of optimization, then we have the momentum, weight decay, mini batch size is actually also always fixed to 128, and then the number of epochs, that in this case is 2. Okay. Well, can run this, but I don't think we need it. So what I tried to do is here was to have to keep track of these things, essentially. The test accuracy for each task over time, the final accuracy distribution, so the Vulkan distribution of the accuracies at the end of the whole training protocol.
By the distribution, you mean over the task?
Yeah, I mean over the task. The sparsity level over time only, this is important, I keep track of the sparsity for now just for the last feature layer. So I keep track of sparsity here for this model. It's the end here. And in the end of the features, let's say, space of before the actual classification part here. So I don't keep track of all of the globals because I wanted to look at just one activation volume and see if things are okay. But at the same time, I didn't want to look at every possible.
Did you use dropout consistently for everything?
Yeah. So like these. So what I do is I can tune this parameter. So that I can put it 0, but in general, in the experiments that I run, I've seen also that it helps. So for now, I kept that as 0.5, I think. But so I'm tracking sparsity level average as the across the batch and the activation volume for each image. So.
Does that include the dropout?
After the dropout. After the dropout.
So it's during the inference mode. Is it doing the training? Because the sparsity will be, if you're doing 50% dropout, it'll be totally different.
Yes.
Yeah.
Yes, it's off the k-winners in the sparsity percentage on, right?
Yeah.
So it's if it is 0.5, probably the dropping out units. Yeah, it's off. So we are going to see that it's off the percentage on the level that I ask through the network through k-winners. Okay, so but what I was saying is that it's not the average across all the possible units in the network, it's the average just on that volume after the features level. So even though, for example, in this case I use k-winners here, I don't keep track of sparsity here. In this case it's just here after dropout, just to make it clear. But I guess, this is, when I was running these experiments, I was thinking, to do this kind of work, it would be like really interesting to have a more, comprehensive analytic tool to look at all the things that are going on into a network. And it's just a bit tricky to do that, like just with plots in a notebook, but it would be like really interesting to have like more of a TensorBoard sparsity tool that you can look into and have in a single web page maybe all the stats that you want without plotting yourself things.
Okay, you want a super plot.
Yeah, that would be interesting. And it will help a lot in this process. But okay, so that was one node. Then what I do is I was also interested to see, okay, but in this level, what's the actual distribution of activations? So it's just it's if we enforce sparsity with k-winners, I thought it was without boosting, but also with boosting, we are really using all the units in that particular feature space, in that particular level. Or it's just like 2 units or 4 units that are active all the time. And so I plotted the number, like an histogram of the number of times a unit get activated through all the training protocol. So at the end, I just plot how many times a unit has been used. Okay, so these are and here I wouldn't want to go into this, but we have the actual plots, definitions. Okay.
We should probably speed up a little bit.
Okay.
Yeah.
It's not a lot to see.
Execute the.
It's okay. So,
Codebase and
yeah,
jump to the next.
the results. Okay, this is the first model we are considering. So these are the parameters I use for this model. So was this one. It's not a CNN. Dropout is 0.5. Just one either layer with 4K units. Learning rate 0.1. I use momentum 0.9 Nestro, and the percentage of this case 1%, right?
No.
0.1. Yeah,
4
1%.
in 4,000.
Yeah.
4 in 4,000.
Yeah, and then with a gain of
What is this first byte false? What is this first byte false?
Oh well, so yeah. I always saying I always compare both models. Have the same model with or without k-winners. So with or without.
Oh,
this-
so sparsify false means
without
there-
k-winners. So
there's
it's
no
like
k-winners.
That's
In
relu
the
of
value.
yeah, exactly. Sorry about that. It's instead of k-winners, it's relu
Okay.
for these two models, and in this case, it's just without k-winners.
Okay. So this one doesn't do sparsity.
Exactly. So just to see, because
It's a
the
baseline,
idea
yeah.
was, exactly, was what we are actually sparsifying is net or not, or what's happening. Okay, so let's see.
So that percent on didn't even apply in this model.
No, exactly. So there are parameters that are switched off.
Yeah.
Why is it
It's another
percent
one.
on a ratio on?
I
Because if it was
didn't
actually
choose the
percent on, it would be
name.
1 in 100,000 units active, right?
Variable names.
Can you talk just a little bit about incremental?
Let's call it sparsity.
How many samples are you averaging?
How many examples?
In each experiment, how many samples are you averaging?
Density.
No, it's just one.
Right.
Just
one
one.
run.
All
I
of
just-
them are just one?
Yeah.
And do you fix the random seed?
Yeah, just the random permutations are fixed and
Or do you fix the random seed for the initial weights of the network?
Oh, that's a very great.
No, it's not fixed the initial weights, but running multiple times the same run, you can have that difference in terms of
That's my
1 to
question. So how many
3%.
times did you run each one of them?
I mean, I just explored that manually, so a few
Ah.
times, and I just noticed that for all of them and all the configuration, you can get a standard deviation from 1 to 3 percentage points. So it's not really trustful for now. It's oscillating a bit, but at least we get an idea. So again, here you can see in this plot the accuracy over time. So you did 10 different tasks here on the x-axis, and the accuracy for each of those. So you can see here the different lines with different colors identifying different task accuracies. And you can see here, for example, after training on the training set of the task 0, you have a very good performance for the task 0. Sorry, the color is not really great, but task 0 here. And you can see that this is going down when we move through the entire training protocol. And you can see that at first you cannot transfer anything to the next task. So, but when you move to the second task, task 1, this goes up. This is normal, but the first, task 0 here is going a bit down, and this is going to be the same for all of the. So you can see here that with this plot that easily see the problem of catastrophic forget, right? Okay. So here it's the task accuracy distribution. So you can it's easy to see in this graph that in the previous one, at the end of the training, you can see that you have forgotten mostly about the first tasks in the sequence. So you have more forgetting on the 0, then a little less on the 1, a little less on the 2, and so on.
And the red line you put
The red line is the average across all those. So this is the final, let's say, metric I'm considering here is not the greatest you can consider forgetting, blah, 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 blah. But it's like saying at the end how much you retain about, because every task has kind of the same accuracy in the end, is kind of the same complexity, so the average is actually telling us the forgetting ratio essentially on the previous tasks. So ideally what we would like to do is to have all these bars to be the same of the last one, and that will mean no forgetting at all. And I didn't put another baseline here, but you can show that it's possible with these kind of models if you train on all the possible, the union of all the possible training set, you can show that you can get to this level. It's not a problem with a particular model capacity or something else. You can do that. It's just the problem of continual learning. And then here, this is kind of nice. So the looking into at that particular level, the sparsity, the percentage on over time. So here you can see 20 different ticks here because we are looking into epochs. We have 2 epochs for each task. So you can see that, for example, even in the first task, you can see that the sparsity level at the end. This is just at the end. It starts from the end of the first epoch. So it means that when it started, it was even higher. And I have noticed this a lot. So you start with a very high dense activation, and this goes down as you move forward in training. And actually, it does that when you train continuously on multiple tasks. So you can see this trend is among multiple tasks. So it's crazy.
Because of dropout?
I don't think so. It's like a normal behavior.
It is normal behavior.
Of the gradient descent optimization that usually
Here's
want to
the
try
question.
different combinations and you remove
If you do this over many trials, can you prove the correlation between the sparsity and the reduction in the forgetting rate? Because it's very clearly obvious that the first task has a much higher forgetting rate. It collapses much faster than the other tasks upon success of learning. So the forgetting rate actually decreases. And the question is, can that be attributed to this sparsity?
That's so interesting. But actually, from this graph, I think that these tasks, the performance of this task is going down the same way, right?
No, it's not. Look, I mean, like that gradient goes like this, right? Whereas these they're like increasingly flatten out.
No, but that's because if you have to see with the same amount of task of time, let's say that these should be
I understand, but like look, within learning one additional task, the first one drops almost 10%. Right? This one, upon learning one additional task, drops maybe 3%.
Right, let's see.
So the learning rate is, I mean, like, we don't see the rest of the graph, but the learning rate, like this, is shifting upwards.
Well, that's interesting. I mean, it can be aligned also with this idea that with sparsity you get less.
That is exactly my point. So can you prove that?
Well, that's something we are trying to do. Right?
That's a statistics question.
I think we should remember we started off saying we can't generalize too much.
Yeah,
on this task. This is a really
absolutely.
bizarro task.
Yeah.
So I don't think we should spend too much time analyzing all of this and trying to do repeated experiments and try to find the slopes. And it's really this is just a code debugging exercise.
Yeah.
Right?
Okay.
And I think we can't learn too much from this about true continuous learning.
I'm sorry, I didn't really get this chart. So why are you showing the sparsity in activations?
Sparsity of.
Non-zero.
I mean, it's the percentage on. I don't know.
Of units, right?
Of units.
Okay.
The
But isn't that fixed because of K-winners?
No, there's no K-winners.
There's no K-winners in this
Dense
one.
network.
exactly. So
But it's not really dense. What he's showing is that it's actually pretty sparse. It's getting down to
that's
2 to 4%.
this is
Yeah.
MLP. Remember that this is a
This is
very
MLP, yeah,
small.
yeah.
It has a dropout in there.
It has dropped.
And that's 0.5.
Sure. I think the biggest thing here is that there's no batch norm.
Right.
I think if there were batch norm, this would possibly be.
Oh, that's right.
Yeah.
It would be 50, yeah.
Yep.
Well, he's also measuring after dropout, which is
There.
yeah.
Yeah,
So there's
it's
that,
a-
half of
Let's
that.
see.
So-
Let's see
gradual
the
dropout.
sparsified version. I have the graphs for that
Yeah,
one.
yeah.
So this is the histogram of the activations at the end of the whole training. So you can see that I don't know you have a unit with the dense version that is activated like only. I mean, this is the minimum number of a single unit that has been activated.
But I'm actually curious also with the previous one is like, do you just end up with a whole bunch of dead units? Is that what ends up happening?
That's
here?
interesting,
Because
because
you have
the-
so many that it's not really that it's sparse.
No.
It's just that you have a bunch of dead units. And,
Yeah,
and
probably.
only a few are really active.
So essentially, you are saying that it would be nice to see this graph at the end, maybe compartmentalized just in every task. Because
what
this
is
is
this?
because
Sorry,
this is a wall across the wall training. So we cannot say that after at the last task.
What is the y-axis here?
The y-axis is the number of times a unit has been activated across the wall training.
Right, of all epochs.
Of the all epochs of the all training.
So there's no that, yeah. Every unit there is 11.
So there's no, so every unit has been used in the whole sequence, but we don't know if if each unit has been used in the last
Oh, yeah,
task,
yeah,
for
because in the
example.
very first
Yeah,
iteration,
yeah.
everything could
Yeah,
be used and
yeah.
then they die out.
But it's interesting that some units are used very few times, so that's
Exactly.
That's maybe a hint about that.
Yeah.
Okay, and okay, so the final accuracy here is just the average is 65%, and here is the actual percentage on at the end of the whole training sequence, so 2.5%, and that is actually like 100 units.
Out of the 4,000.
Yeah. And we can go faster here, but what I changed here is just the sparsify too.
It's still.
It's the same, it's exactly the same parameters.
Still 1,000%.
Here, you can see that you're forgetting is much less. This is the distribution.
Very nice.
And here, this is the sparsification. This is the.
Oh, beautiful.
And here the final accuracy is 86, so it's very strange because you have just 2 units activated, because we have enforced these kind of. This is the after dropout. So in the end, it's just after the dropout is like 2 units active. So it's very strange.
I mean, I think the question, of course, not be if you would have that animated over the episodes, right?
Yeah.
How this changes.
Look, yeah.
How does it look?
Absolutely.
Is it actually like a tear down of
Yeah.
some units, or is there some switching anyway?
Yeah.
Can you zoom in on that plot?
No. I mean, I can do you want to? Well, I guess.
I'm curious if in this case there are that unit. I can see.
Well, here it says like 493,
493,
never activated.
Oh. You have.
Yeah, but we can play with these.
Out of 4,000.
We have the data.
10% dead.
Yeah, that's a concern. Okay, then moving faster to the second. In this case, I don't plot everything again. It's just to see that we can have for the well, parameters are kind of the same here. It's just that we have 2 hidden layers of 4K, and then we have the first, model that is dense. The second one here.
This is also
that
dense.
part.
This
So
one.
this is dense, and,
Yeah.
and these are the let's say stats for these.
Yeah.
So all the units are used, kind of the same as before, but we end up with a 47% accuracy, so even less than before. And then here the percentage on is much higher. We just added a delay, and this means like 500 units out of 4K of the last parameter that we are just looking at the last delay. And for the sparse version, we have a few hidden units that are not used. Okay, and final accuracy is better, still better, 61 against 47. But in this case, it's the
You
same.
have more units. You say you're measuring the CNN, you're measuring at a different spot, right?
But this is not
Just-
CNN, this
just
is
the
not
last
CNN
layer.
yet.
Yeah, it's not the CNN, it's
Okay.
NLP, and we are measuring sparsity level only of the second hidden layer after dropout.
This is the 2, MLT2.
Yeah, that where the arrow is there, is where we measure things. But you can expect these things also on the previous hidden layers as we are enforcing K-winners here and dropout. Okay, and then for the CNN, let's see, the CNN, okay, CNN2 here, and so we have a like, this is different somehow. We have a lower number of hidden units. We just work with this way, so I just thought it's better than 4K units. And here, so without sparsification enforced, we have this kind of very low percentage on active units, 52% of accuracy, and this is the number of this number is I here because we are looking after on the volume after the convolutions in this case, and we are also sparsifying local k-winners.
But there's no, this is no sparsity.
Sorry, yeah, this is no sparsity. Oh, that's great. And then for the sparsified version, yeah, we have. I mean, it's
A little sparser.
a little sparser, yeah. A little better in terms of accuracy, like a percentage points better, but it's not just a little sparser. But what I noticed is that we are enforcing this sparsity level from the start, and that's really different from what you have with this kind of sparsity level going down across time. In fact, as a counter experiment, I just tried to have a very high k-winners. In this case, we have rel. So the idea is that if you put the k-winners level very high, you shouldn't compromise the results. It should be the exact same of the dense counterpart. So I tried this, moving like little by little this threshold for the k-winners from 2.5% to I don't know 50, and it was still hurting performance. So I had to go like higher at 60 to get the same accuracy. So it means that this process is important somehow. And it has an impact on the idea of changing sparsity across
I'm not
time.
sure I follow, but okay.
Can we learn this as well? Like instead of fixing percentage on k-winners, can we learn this and train? Which one would be that?
Yeah, adaptive sparsity,
Yeah.
right?
I was
What's
thinking
the-
this issue, yeah.
No, but my question was because in the end you have kind of the same sparsity. What's happening? What's
You need to start.
You need to start very dense.
It reminds a little bit of simulated annealing, but instead of decreasing a temperature parameter, or like a temperature curve that you're tapering down, you have a sparsity that you are sort of like dialing up, or like what you're like decreasing
Yeah.
the percentage on.
So that was just something I considered. Then I tried from these CNN parameters that you can see here. So the sparse version, this CNN, parameterization, configuration. Then what I try to do is to remove, one element.
Can you go back up? What is the sparsity level here? Percent on is 0.05. And how many channels do you have?
64.
64. So it's 5% of 64, which is 3,
Yeah.
basically on. Okay. At each
And this is
location,
the-
you have 3 on at each
Yeah.
location.
Yeah.
Okay.
And this is the final.
Yeah, for that I can see why ReLU would be important.
Okay.
Or MNIST. Yeah, because you have a lot of zeros coming in.
Yeah, and these are again, taken with a grain of salt, and et cetera, but these are the results when you just remove that feature, and then when you move down on the table, we don't remove dropout plus momentum. It's just, the previous configuration, we remove just momentum. So I didn't try all the possible configurations, but just one thing. So dropout seems to be, to impact a lot the performances. This is just for the sparse version, but it would be also nice to add the results for the dense, with respect to the dense counterpart, because when we remove dropout, how does it affect the dense network? It's important, and how does it affect the sparse network is important as well. So in this case, just the sparse version I just reported here, and it has a very it's a very important, I would say, negative difference here in terms of accuracy. But this is also, dropout was already shown to be important for continual learning, so I don't know if this is really related to sparsity or just related to continual learning. So the dropout can help, in general, not to overfit, can help, to avoid forgetting in continual learning. This is a vision in many papers in the past. So yeah, we should look into the dense counterpart to actually understand if it is it's just helping the new learning, or is it also it's helping more maybe the sparsified version or not. So for the momentum decay here, we have also an impact on the accuracy. This is very interesting actually, because so what a note that I put here was that if I remove momentum and L2 regularization from the dense
counterpart, I can get even better results. So we lose this advantage of sparsifying essentially with k-winners. You know, all these configurations where, okay, I mean, we could have the same level of, you know, better accuracy with a more sparsified network. But in this case, when you remove momentum and decay, I found that you know, you could actually go even better than the sparsified version.
How do you make
So
understand that?
I think that it's very difficult to understand in details why this is happening. But my idea is that decay actually is decaying the weights that are not really important for a particular task. When you go across this task, and you tend to erase, erase or change the weights that were important. You learned before, but are not important anymore in the actual in the actual optimization of the current task. So I guess maybe that's related, I don't know. But on the other hand, decay was also shown to be important in terms of generalization and avoid overfitting, and that also helps in continual learning in general. So it's difficult to interpret in this
But
way.
you can't see overfitting because you don't have a validation test set, so to speak.
Yeah, I mean, we can look at probably.
Like you're measuring the accuracy on the.
Yeah, I mean, also you have an
you're measuring the
configuration on the
accuracy
test
on the
set.
test set.
Yeah, on the test set, but you'll never know. I mean, if you are still overfitting the whole data set actually,
Right.
because when you are tuning these hyperparameters, you are overfitting also the test set. So
Yeah.
you'll never know. And we played so much with MNIST that we have research example already.
You are overfitted too.
Yeah, I mean, it's impossible not to overfit MNIST.
They permitted them, yes.
By now it's impossible not to overfit.
Okay, and then for the momentum explanation, also in this case, I think momentum is pushing hard on the current optimization of the specific task. So maybe that's not helping continual learning. Because you're moving faster in the direction of the gradient, so a bit of randomness maybe can help. The fact that you don't want to raise things that you don't see anymore now, but you've seen in the past.
So are these set so that as you run through the tasks, you set this particular rate, or you kind of reset things up for each task?
No, exactly. You see, I let the optimizer go.
Okay.
That will be interesting to just reset the optimizer after every task to see the impact of that.
Again, I wouldn't spend a huge
Yeah,
amount of time
yeah,
on this in
exactly.
this
Yeah.
pretty artificial
Yeah,
task, and
absolutely.
I think there are a lot of issues in setting up
Yeah,
the network and other
definitely.
things too. So I wouldn't draw too many.
And then
conclusions.
for the k-winners, I removed the k-winners local in the CNN, and I put back the local version, and it was beneficial in this case to have the local version, 5% accuracy, and the radio also had a little impact. I don't know if that counts as an impact, 3.4%. As we were saying, it's a bit. We should take the average of that.
It might not be a coincidence that the momentum and the decay
Mm.
kind of go hand in hand, because
Yeah.
like when you have all these, if you think of it, like you have all these weights that are kind of each dedicated to, like this weight is dedicated to task number 2.
Yeah.
It's only there for task number 2. When you're doing all these other tasks, weight decay is going to just keep pummeling it.
Yeah.
Momentum's going to compound that pummeling, and it just like, it just can destroy it, those two
Yeah.
with their
Yeah.
powers combined.
Yeah.
So another few notes. So yeah, especially linear networks. Okay, this is something we already considered, and then something that I wanted to point out is that in this case, momentum and L2 regularization destroy essentially the advantage of using k-winners, but they are needed most of the times when you tackle more complex tasks. So the idea of having a network that does not use at all momentum L2 regularization is a bit, maybe it's not really realistic when you move to more complex
So you're
tasks.
hoping that changes once you get away from the story example.
So yeah, exactly. So the idea is that, okay, even this configuration with all the problems and errors also I made with the boosting and stuff, if we could scale these advantage essentially also to be connected, so that would be great. And then open questions, can we scale these results in networks and more complex tasks? So another question is, do we really need to sparsify the network from the start, or we can just care about the percentage at the end of the task?
That's a weird question to me because we're dealing with continuous learning.
Yeah.
So there's no sense of the end.
Yeah.
Right?
Yeah,
It's just like well, you want to
No,
be able to, you want to
it's
remember
more-
things along the way without
Yeah.
forgetting them.
Yeah,
So
it-
the end percentage, what shouldn't tell you what's happening in the
there's
beginning,
no,
right?
yeah, no, what I was more maybe thinking is that maybe should we allow, for example, in some specific, in a very small time window, to get the best advantage from graded descent optimization, to leave the network more free to explore things, and then to reduce, after a while the activation, the dense activation to something we care about, is something that is more specified. So that was just the idea. If we can consider having at some point in time a little bit of more degree of freedom for a network to have more units activated, and if that can help also continual learning and in general us.
Maybe. It's weird. I mean, when you think about continuous learning, you can't think of it as a batch system.
Yeah, absolutely.
Right? And so, also, I think the point you made is really important too about this momentum and weight decay and stuff. Is just really fighting against the whole spirit of continuous learning.
Yeah.
Like if you learn some things in the beginning, you don't want to touch them. Right? Otherwise, you get forgetting. Also, almost by definition. You want to really leave those alone, and I wonder if any type of regularization will have this kind of
Well,
effect.
like elastic
right?
rate consolidation kind of probably. If it's a regularization which is aware of the other tasks, then you don't have to teach it. Right? That's what EWC does. Or
So of course,
Right, right.
the regularization, especially from the past, were taught about a machine learning setting which we have ID data.
IID data, yeah.
So
exactly.
that's the problem, and I think we can change that, and but the problem.
But also
of using
dense
machine learning-
IID data, because I
Yeah.
think momentum
Yeah,
with
right.
sparse weights is
Yeah.
really suspect too, and sparse activations.
What would happen if you keep cycling around on the tasks, 1 through 10?
Because it's a little bit like the replay idea, right?
Yeah.
You keep throwing the old stuff back
Yeah.
in, and that helps, that works.
Yeah.
I mean, if you train on the entire thing completely, it works.
Right.
So it's just, and this is the other end of it, and so anything in between will give you close.
It's like
like
if you
cheating.
Huh?
It's cheating.
Yeah, it's cheating in continual learning.
So, the sparsity thing, what you mentioned, like starting dense, becoming sparser. One thing we could connect that to is if something is kind of more of a novel stimulus, if it's unlike what you've seen before, then it might be somehow be allowed to be more dense, and then better it becomes sparse. And you might already know that I'm thinking of Michael Berry's stuff involving novel stimuli with the study involving novel stimuli have this initially dense representation in the visual cortex, but then it becomes sparse after it's seen it a few times.
Yeah, it's hard for me to relate that to, because that's more in a streaming predictive kind of scenario, and then I think about it in terms of the temporal memory
Possibly.
context,
That
and
was
static
always-
kind of scenario.
That was always in the air, whether that was temporal in their
Yeah.
paper, but yeah, you're right.
But it could still be that density. If you think about unions of representations, then if you have something that's unknown and having a union to represent the stuff that's unknown, I think that still makes sense in the static.
So is that April's novelty determined from explicitly known from the input, or was it just inferred from how things activate in the network?
So they were recording mouse visual cortex, and they were showing the mouse various stimuli involving Gabor filters and various configurations.
Okay.
And,
So they're reducing the novelty.
yeah.
But it's also not clear whether that increased activity is because of stronger reduced sparsity, or whether it is just higher firing rates of the units that are active anyways. So, is it just sort of
Yeah, I'm just trying to figure out what would
Like
be the
that
equivalent
to me is
model
clear.
in our networks, to replicate that property.
Sorry that I kind of hijacked it, but just to answer that question, they were doing actual spike sorting, and many more units were active for the novel stimuli.
So not just higher firing rates, but also more active units.
Yeah.
Right.
Yeah, in fact, they couldn't do firing rates, I think, because it's calcium.
Correct.
Okay, so
My big suggestion here is, before you do any of the stuff here, I think you should really think through the setup
yeah,
and the parameters, and try to get into a regime that we think will work well.
yeah,
And
And if you just do black and white, it's almost the same size. It's the ratio by ratio image, so you can
Yeah.
use it.
That's why you're yeah. Yeah.
Yeah, it's split into 10 groups of 10. Every computation will be like almost the same.
But the one difference here was you were using the same classes again and again, right? Were
Yeah.
you with,
In that case-
you're talking
In
about
that,
software,
in
you're
that
talking
case,
about
you split into 10 groups, and then you first learn 10, then learn 10 other objects.
Yeah,
then
you have
10 other
100
So you're talking about different, okay, it's
Yeah.
still kind of a different experience.
Yeah,
Yeah.
you have to be really careful that, in that case, if you, when in the second group of 10, that you don't back propagate through the first group of 10. Right, when you,
Yeah, you have
right?
different, you do
Because you don't want
blends,
to,
you mean.
right?
You have separate classification layers.
I think so,
Yeah.
yeah, it's- yeah, exactly.
Mostly the people do that.
Do that, yeah. You don't just set up a
All right.
flat group,
Yeah.
Just train normally. I
So
think
the,
just
the
treat
feature
it.
extractor is the same, then you have a final head, they call it a multi-head
Yeah,
approach,
yeah,
which have
exactly.
different classification layers that are completely separated.
Yeah.
So you need, actually, when you test things out, you need the task label. So you need to, if you want, if you want to compare, the right class, you need to know what kind of task you solve.
Right.
Well,
Well, yeah, that needs some thought too.
Yeah, that's
That's
what,
weird.
no, it's what people do. It's a multitask, very
Yeah.
hard for continual learning, and in that case.
I mean, I think you can still look at all of them and see which one's the
Yeah.
highest motivation.
Yeah, I mean, that's, let's say the naive approach is without task labels, is that you just inference all the possible S and then you pick the maximum, but I don't know if that, yeah, the
But
problem is
that
that you
actually
don't
work.
see, yeah, because you don't see, essentially you don't see, you're not comparing the first 10 classes with the following classes. So
Yeah,
they're
yeah.
not tuned, the weights are not tuned so that, you should calibrate this response of the network. So that in the end, the final, softmax maybe that you put on top of
Yeah.
everything is valuable. It's
So what happens if you don't do a multi-head, if you just do this standard, have everything on?
you have kind of really conservative forget, because when you move to the second task, maybe you just use the second 10
10 over and over again,
and
yeah.
the other one is gonna, the other weights are going to be
Wipe
belong
everything.
to minus, I don't know, some
So that's-
very big values so that the softmax.
Yeah,
is-
so I can see that in a dense setup,
Yeah.
but in a really sparse setup, that may not happen.
Sparsifying the output layers.
Yeah,
So,
but no, but even the intermediate layers are really sparse, the error is not gonna go through all the way. from
Yeah,
those
that's
areas.
true for the feature, let's say, space level.
Yeah.
But then for the problem is in the output, right? The weights connecting to the weight that the
Yeah, that'll get-
neurons that are not
those will
active.
get decimated.
are gonna be- Yeah,
Yeah.
that's right. You need a really a few integration. Okay.
Cool, thanks.
Thank you.
Seems like this can go places.
Someone from Rome says hello.
Hey!
That's how I say ciao.
Yeah, I said ciao. I said un saluto de Roma.
Crazy.
Okay, so we're
Well,
going
thank
to
you.
shut off the stream.
Great.